Okay, so thank you very much for the invitation to come and to talk. It's a beautiful place, and thank you all for coming at this hour. To be quite honest, I don't know if I would have come to this talk at this hour if I weren't the speaker. Okay, and everything I'm going to talk about today is joint work with Ofer Zaytouni, also from Weizmann. Okay. So before I start the introduction, let's start with the problem. So you have something to chew on while I give general introduction. So you look at a random polynomial with coefficients plus or minus 1, I going from 0 to n. Okay? So this is the definition. Okay? And we take two polynomials, independent, and having the same distribution. So both polynomials, so we have like two n plus 1 random signs, and you create from them two independent polynomials. And the question I'll discuss for most of the talk, what is the probability that there exists some psi which is a common root? And just to fix notation, complex is good. So I'm not restricting to real roots or anything like that. Of course, asymptotically, is n going to infinity. So I think the question is formulated in a unique way. And so before I start revealing the answer, let's remind you some general things which are known about a single polynomial which is of this type. So the distribution of zeros is very well known. It's something which has been researched a lot, and it's known that the roots are essentially around the unit circle. So in fact, you have an annulus, which is approximately of width 1 over n, where most of the zeros lie, most of the roots lie, with exponential decay as you go away from the annulus. And the zeros are distributed more or less uniformly on it. In addition, you have something like approximately log n real roots. So if you want to have some picture of mind, how do these roots look like? This is where you find them, around the unit sphere, concentrated very strongly. So these results are due to Ibragimov and Zaytouni. Probably have the year too. No, I don't. Okay, so let's go back to this question and see what, and make some preliminary considerations. So first of all, it's clear that the question is pointless unless you take the random variables to be atomic, as I did. If you take them non-atomic, then this probability would just be 0. Okay, so this is why I'm interested in plus minus 1. So plus minus 1 is kind of a canonical atomic distribution. So let's start with just examining values of xi one by one. So let's start with xi equal to 1. Okay, what's the probability that our common root is just 1? So what is the probability that 1 is a root? Just the probability that sum plus minus 1 is 0. This is simple random walk of length n, or n plus 1, whatever. So this is some constant over square root n plus some lower order terms. This is just for one polynomial. So for both of them, you get constant over n plus some lower order terms. So we already have a lower bound. Maybe I'll put here some more space. So we already know that it's bigger than some constant over n. C equal to minus 1 gives you the same contribution, because basically it's still random walk. And also, so the constant here can be calculated explicitly. It's something like 4 over pi or something like that. So 2 over pi, but when you add this, so this kind of, the difference between 1 and minus 1 is important if you're interested in the value of the constant, which I kind of wrote, but I don't feel like talking about it in the end. So let's drop that. Now let's take a third example, which is, I think, illustrative, is that C equal to I. So let's see what's going on. We need to take the powers of I in this expression. Maybe I shouldn't have used I for the index. This is going to play an important role. So, so you take powers of I, and it's clear that that basically the evens and the odds are completely independent. Okay? So basically, what you have here, the probability that sum plus minus I to the k is just equal to the probability that the sum on all k even plus minus 1 is equal to 0 times the same probability for the odd. So you get a much smaller contribution. So this is something like constant over n. Again, let's ignore issues of even and oddness of n, right? It's 7 in the 9. So we can assume all n are divided by whatever you want. Okay? So you get constant over n for one polynomial. So you get constant over n square for both of them. So this is obviously a lower order contribution. Okay? So you already have a rather interesting connection here, that it seems as if the algebraic degree of xi plays a role. Okay? We see that 1 and minus 1 behaved like a one-dimensional random walk, but I behaves like a two-dimensional random walk. So we could imagine that maybe algebraic, if you have algebraic degree d, it behaves like a d-dimensional random walk. So let's define algebraic degree, since it's 7 in the 9th. So I think everything should be defined, even what is I, the square root of minus 1. Okay, so what is the algebraic degree? So the degree of xi is equal to the minimum of the degrees of all the polynomial. So the degree of the minimal polynomial that xi is a 0 of that. So the degree of the minimal degree of xi, of course, I'm taking q with rational coefficients. Okay? And this is the same, this is a very standard fact, is the same as the dimension of the span of psi I, psi to the k, k from 0 to infinity. Span is, again, with rational coefficients. And these are standard facts, and actually this particular one is not difficult either. So you want to see whether to understand a bit the connection between the degree of psi and the probability that this sum is 0. Okay, and this is, has been researched quite intensively. This is known as, in a more general setting, this is known as the Littlewood-Offord problem. I hope I didn't misspell Offord. No, seems correct. If I did it twice. There's also a Littlewood-Offord problem and an inverse Littlewood-Offord problem, and I can never remember which one is which. But essentially, the problem is as follows. You have some numbers, A1 up to AN. What can we say about the probability that sum plus minus AI is equal to 0? So generally, we want a connection between properties of the AI and estimates for this probability. So this is, of course, more general because I'm not assuming these AIs are the powers of anything. So the first result, well, okay, second, first one was due to Littlewood and Offord, is due to Erdash, 1945. And he showed that if they are all different from 0, which is kind of a natural assumption in this problem, then this probability is smaller than a constant over square root. So somehow the situation where they are all 1 is somehow, well, this is just claims that it's asymptotically maximal. It's actually just maximal, but I don't remember who proved that. In fact, maybe I never knew. Okay. Now, in this setting, in this general setting, though, there is another example, a very natural example that you have to keep in mind. This is wet. You warned me about that. Okay, so, and the other natural example to keep in mind is just these numbers. Okay? So when you look at, you ask what is the probability that sum plus minus k is equal to 0, then this is approximately here means up to constants, n to minus 3/2. So it's an important example to keep in mind. Heuristically, this is clear. Why should it be so? Well, what's the variance of this variable? The variance is just the sum of variances, which is just sum of k squared, which is approximately k to the third. So the variance is approximately n to the 3. So it's natural to assume that if the variance is n to the 3, then the probability of every singleton would be approximately n to minus 3/2. And it's not difficult to prove with Fourier transform. So you just take Fourier transform, and it's more or less like a standard, the standard proofs of CLT work. But this example really makes the formulations of all the results much more complicated. So, okay, now I definitely need my notes because I have to spell some Hungarians' names. Okay, so a result from 1965 of Sarkozy and Semeredy. So, says that basically if they are all different, then this is best possible. So, circle Z, and ready. If AI are all different, then this probability is smaller than some constant over n to the minus 3/2. Over n to the 3/2. And actually, well, okay, this is getting a bit into the exotic, but in 1980, it was actually shown the exact maximum was actually, it was shown that it's actually the maximum. So this, by the way, is Stanley. 1980, if for n odd, then minus m up to m is maximizes the probability. Okay, and this result is, I haven't actually read it, but it's supposed to be a rather impressive application of algebra to combinatorics. So definitely the title looks like you're in for a wild ride. Anyway, so this is some of the history of this little Rutherford problem. And the result that I'm going to use is the result of Tao and Wu, rather recent, from 2009, which more or less gave a full classifications of when this should be small, when this is not too small. Okay, and I don't want to state the result completely because of this example, the formulation becomes rather messy, and you need to define what is a general arithmetic progression. Who knows what? Anyone who knows here what is a general arithmetic progression can kind of guess how the formula, how the theorem might be stated. Anyone who doesn't is not missing on much. But so I'm not going to state it. Definitely not at this hour. But one of the corollaries, a corollary from that is exactly what we claim, what I suggested should be true. If the algebraic degree of Xi is bigger or equal to D, then the probability that sum plus minus Xi to the K is equal to 0 is smaller than a constant over n to d half. And unfortunately, the results are not as sharp as those, so there is a minus O small of 1 here. But other than that, they are as sharp as you can get. Okay, is this corollary clear? Again, the degree is this degree, the algebraic degree. Okay. You're behaving yourself. Maybe you'll get 5 minutes off. Okay, so now we can let me finish. Let me finish the proof of the one variable case by reminding you. So this is a very good estimate, but you can't just count over all numbers, right? Even if you just restrict yourself to algebraic degree 1, there are still infinitely many numbers. You can't count on them and use the union bound. So something else must be said. And I need to remind you what's an algebraic integer. For those of you who ever knew it, for those who didn't, tell you. So an algebraic integer. So the definition of an algebraic integer, we say that Xi is an algebraic integer if there exists a polynomial which C is a root which has integer coefficients and is monic. So what does it mean? So it has integer coefficients, everyone knows. And monic just means that the top coefficient is 1. Okay, so this is called monic. This is just a definition. Just from the definition, it's not even clear that not all algebraic numbers are algebraic integers, of course. It's not true, but in order to actually be able to use this, you need an equivalent classification which says that an algebraic number is an integer if and only if the minimal polynomial that satisfies it is monic. So this is already a theorem. Let me not state it. If and only if the minimal is monic. And again, when I say monic, I mean with integer coefficients. Otherwise, it's completely meaningless. You can always multiply by a constant. So, how will I use this notion? Well, the size that interest us are obviously algebraic integers, right? Check this polynomial out. The top coefficients is either 1 or -1. If it's -1, I can multiply by -1. So the size that we should even start to consider are algebraic integers. Okay. So, for example, let's start with the case degree is equal to 1. What does it mean? It means that there is a minimal polynomial ax plus b equal to 0. Let's call it psi. We are interested. Okay? But it should be monic. So a should be 1. So this means that psi is an integer. So a rational number which is an algebraic integer is an integer. Here is your proof. And so what can we say about integers? So here is the second observation. Every number which if psi satisfies such an equation, then it has to be between 2.5. Right? If it were 2 or larger, then the top coefficient would be bigger than all the rest, and you'd have no hope of it being 0. If it would be half or smaller, then the bottom coefficients would kill all the rest. Okay? So an integer with absolute value between 2.5, that doesn't leave many choices. Okay? I'll leave you as an exercise to make a full list. Let's go to the second degree. What if the degree is 2? Well, now our minimal polynomial is x squared plus ax plus b. Now, this is the sum of the roots for harmonic polynomials. And the roots, both of them, are between 2.5. Remember, if this is there is something hidden here, right? But the point is that if this is the minimal polynomial which satisfies psi, then any integer polynomial where psi is a root, the other one will also be a root. So both roots are between 2.5. So a must be between 4 and minus 4. This is a product. So for the same reason, has to be between 4 and minus 4. And yeah, something like that. And so there are 49 possibilities. In fact, much less, but there is a number of possibilities which is independent of n. I really couldn't care less if it's 49 or 49,000. Okay? So each one gives a contribution of a constant over n square. It's not written anywhere, but anyway, each one gives a lower order contribution, and the number does not depend on n, so it's a lower order contribution. Same is true for degree 3, degree 4. You're probably wondering if I'm going to list all the numbers. I'm going to stop at 5. Why can I stop at 5? Because at 5 I can use the following argument. Suppose let's look at the first polynomial. It has only n roots. Each one, if it's of degree bigger or equal to 5, then the probability is smaller than a constant over n to 5 halves. Right? I check each one. I take a union bound. I get a lower order term. And this is basically all the proof of the one-dimensional case. So all you need to know, basically, is what is an algebraic integer. And then you can go home. Questions on this part? Everything is crystal clear. OK. So I'm sure you all believe that you are already entitled to go home. But let me talk a bit about a multidimensional version. This also has a bit of something to teach us. Okay, let's say 2. So suppose you take now polynomials in 2 variables. You take 3 of them. You ask, what is the probability that they have a common root? Give me a number, a letter here. S. Okay? So let's say so the same preliminary considerations as before work here, because these vectors, each one gives a probability of basically a constant over n to 3 halves or something like that. So the problem is only to somehow analyze the rest of the terms. Okay, the analysis is going to be rougher, but there is something to see. So let's see how it goes. So now suppose you have, let's look at the common zeros of the first 2 polynomials. Let's call them z. Okay, this can be, well, you definitely expect it to be just a discrete set, but nobody is promising you that. Okay? So we have to divide into cases. It definitely cannot be all of them, so there are only 2 cases to consider here. So case 1, z is discrete. And the case 2 is that something bad happened. There was some kind of unusual event. and the dimension is 1. So it's some kind of curve in C2. Okay, so I don't feel like talking about this. It's not significantly different than what we did. Okay, the algebraic integer trick does not work anymore, so you have to use the tau and vu in a more sophisticated way. Let me skip all that. It's way too late to show the same thing twice. I'm not sure if it's not too late to show the same thing once. So let's see what we can say about this case. We want to show that this is an unusual case. I mean, I just stated it as unusual, but that's just a heuristic, right? We expect somehow two generic polynomials to have a zero-dimensional intersection, but as the whole point of this lecture is that there is nothing promising us that two plus-minus random polynomials are generic in any sense. So we really have to somehow do something specific. Okay. Anyway, let's assume if z intersect the line x equal to 0, then everything is good. Why? Because if it intersects this line, then this means that you throw away all terms where k is different from 0, and you're back at the one-dimensional case. This means that P1 and P2, restricted to the first n coefficients, have a common root. We already know that this has a small probability. So, okay, maybe I should write it this way. Probability for two variables that z intersects this line is basically equal to the probability for one variable of what we already had, which is smaller than a constant over. But, and the same thing if it intersects the y equal to 0. But unfortunately, it's not true that all one-dimensional varieties intersect the lines, right? If you take the yx equal to 1, and this is a couple of hyperbolas, which don't intersect any of the lines. Even in the complex plane, doesn't matter. Okay? So what can we do in this case? So they don't intersect the axis, but they definitely converge to them at infinity. So there's a thick hint here, which we should consider infinity, and maybe add it to our space. There's another thick hint to that, by the way, in the one-dimensional question. Maybe I'll skip that. Okay. So how do we do that? Maybe I won't skip it. So what happens? How do you look at infinity in the one-dimensional case? Well, everyone knows that. You have some polynomial, some akx to the k. You want to consider it at infinity. So you write this as 1 over x to the power k. But we are only interested in the zeros. So we can multiply by 1 over x to the k, and we get some a k 1 over x to power n minus k. Okay? So basically, looking from infinity, you get the coefficients are ordered oppositely, which is great in our case because it has the same distribution. Not the same polynomial, of course, but it has the same distribution. So this is the second hint that we should look at what happens at infinity. Now, the correct analog of that in multiple dimension is to consider the projective plane. Now, I'm sure you're all very happy to see this sign on the board. What is the, but there's just no avoiding it. That's how the proof goes. technically, I have time to define the projective plane and prove to you everything. Yes. But maybe I shouldn't. Okay, let's draw some pictures. You know, that couldn't be too bad. Okay, so what is the projective plane? So formally, this is very simple. This is the set of all triples, which are not all 0, which are not without this line. Well, it's the set of lines. So you modulo the relation that x, y, z is the same as ax, ay, az. So this is just the set of lines in 3 dimensions. So it's a 2-dimensional manifold. So if you want to have a picture, well, it's, well, 2-dimension, complex 2 dimensions is 4 dimensions. I can't draw that, but at least 2 dimensions. But you can get a good picture in the real case. How does it look? It's homomorphic to a disk where you are identifying antipodal points. So you take a disk, but in the boundary you identify this point with this point, this point with this point, this point with this point. So it still doesn't embed into 3 dimensions because it's not orientable. If you have a vector, let me draw it like this. If you have like a vector that goes here and you start rotating it, rotating it, rotating it, you reach here, it points here. Now you have to jump here, it points here. You continue rotating it, and it points in the other direction. So it's not an orientable manifold, so you cannot embed it into 3 dimensions, but other than that, it's really a very nice manifold. And you have the beautiful theorem, which is called the projective dimension theorem. What does the projective dimension theorem state? It states that if you have 2 varieties in the projective, in general, in the nth dimensional projective space, and if the sum of the dimension is good, then they intersect. So you cannot have these examples in the projective plane. If the projection in a 2-dimensional projective plane, if you have 2 curves, they must intersect. One at some point. There is no avoiding it. It looks very strange when you first think about it, right? What about x equal to 0 and x equal to 1? How could they intersect? So, but you draw 2 lines, and then you have a feeling they might intersect somewhere at infinity, and they do. Okay? So, and I guess I'll skip exactly how you use it. You have all been very nice to me, and I really don't think the calculations will make it that clear. So, so basically the proof goes as follows. You say as follows. If it's a 1-dimensional variety, it must intersect this variety in the projective plane, which basically means that this bad event, this 1-dimensional common root, will happen in one of the 3 pieces that the projective plane is made of. It's made of, as a manifold, it's made of 3 pieces, each of which is 2-dimensional. Okay? And then what it shows, and really, once you know once you know this theorem, it's an exercise everyone can do at home. Exercise. The probability that z is 1-dimensional is smaller or equal than 3, actually 2. Again, for 2 variables, then this probability for one variable that two polynomials have a common root. So at 3, I might have shown you in the calculation, but I think at this point, this is enough. So what is my take-home message for you? I guess my take-home message is the following. It's enough to know very, very little algebraic geometry to be able to get rather nice results. At least I think they're nice. No. You get results which you yourself think are nice. I think it's an achievement in its own right for most people. You don't need to know, I mean, you know, we are all scared of algebraic geometries because they say things like D modules and a Tal cohomology and so on and so forth. But, you know, the classical theory is just about zeros of polynomials, and it's useful. And it's worth knowing. That's it. Yes. Yes, yes, yes. Definitely the lower bound here. In the multi-variable case, the lower bound is much worse than the probably true answer. So I guess I mostly was, but even just showing that it goes to 0 is not obvious. But yes, in the multidimensional case, I don't have like the exact asymptotics. Should be what? Probably.